Connect your streaming software to go live, mi dice.
Ok, allora io qua l'ho fatto partire. Dimmi se mi vedi.
Ecco, excellent connection, dice che vai, ci sei
Ci
live.
sono. Perfetto.
Non mi muto.
Ok. Guys, a sec so that I can see the chat also in the meanwhile. Nice. Okay. Okay, now you can switch to the live, I hope. Wait up. Okay. Nice. So I see that you guys arrived more or less 10. Let's wait just 1 minute to allow everyone to connect. Okay. So let's start. So, in the second part of the lecture, as we say to you, we will speak about a SLAM system implemented through a Kalman filter. Okay, I would like to thank my ancestors, let's say, Bartolomeo della Corte and Dominic Schlegel, for the specific design of this exercise. Okay, they are the previous PhD of Giorgio, my mentors. So, EKF SLAM. So what's the difference with what we see before? In this case, we are estimating also the position of the landmarks while we estimate the location of the robot. So the map is not known anymore. We will still assume that on each landmark have assigned a unique ID so that we can recognize that specific point, but we don't know where the point is in space. This means, as we will see, that the state actually is growing over time, because every time I observe a new landmark, I have to add that inside my state because I need to estimate this position over time. Okay? So the usual outline, so describe the scenario, then we have to define our new state, which will not be the same as in localization because now we have the landmarks in the state. The controls, that will stay the same because we assume always to have the same robot, so a differential drive. Define the observations, transition model, observation model, dimensionality of the Jacobians. So always the same schema as an algorithm. Okay. So we have our Orazio moving in the 2D plane, is controlled by the omega as usual. Now we can sense distinguishable landmarks, but the location is not known in advance. So we are performing simultaneous localization and mapping. Okay, so we estimate these landmarks while we localize. Okay, so approaching the problem. I already said whatever we have to say. Actually, you might think that SLAM is it's highly complicated, like as a problem. But actually, the fact that the position of the robot and the map are highly correlated, it actually helps during the estimation process typically. Okay, so in this algorithm, the inputs are always the same. So we have the same inputs as in localization: velocity controls, landmark measurements. In this case, we came back to the setting where we can perceive 2D landmarks directly, so there is no bearing involved, no range involved. It's a straight 2D landmark. Okay, so we have a point sensor in this case. So the AKF schema, that's the thing that we see until now. So we have our transition function, that's the Jacobian with respect to the state, Jacobian with respect to the control, and that's how our covariance propagate during the prediction step. In the correction step, we compute the Jacobian of the observation model, and this is how we update both the mean of the distribution and the covariance. So As I tell you in the introduction, in SLAM, what we have is that while we are moving, so while we are observing things, we have to extend our state. So every time we see a new landmark, we have to insert it inside our x vector, so inside our Gaussian distribution. And these landmarks are going to be refined by successive observation. So the estimation of the position will be more and more accurate. At the same time, having an accurate position of the landmarks helps the system to localize. This is, for example, what we see in localization. When you have the known position of the landmarks, you need really few observations to get a small covariance, so to get properly localized. So the game here is to try to do both things in parallel, okay? And this point is really important because we will see it also inside the practical aspects of this exercise, that we have to manage this extended state over time, okay? The extension of the state over time, for better saying. So let's define the domains. So as usual, we have to define the state, define the controls, and define the landmarks. Now we will focus a bit on the state space domain, because we have, as usual, the state is an element on SE2, but we parameterize it with an R3 vector. But now we have those guys. So inside the state, we have to add the 2D position of the points of the map, okay? So our complete state in each point in time will be the current location of the robot and the set of landmarks that I observe up to that specific time instant, okay? So the dimension will be 3 plus 2n, where n is the number of landmarks that I observe in a time instant, up to that time instant, okay? So until time t. So for controls and measurements, actually nothing changes because we have the same robot, so same commands, translational velocity and rotational velocity, and we have a point sensor, so we are still observing a 2D point. So the only thing that we have to modify is the state, and regarding to that, we have to manage the extension of the state over time. So that's the main difference with the localization exercise that we see 2 times ago, let's say. Okay, so we define the domains. Now we have to define transition function and observation function. Okay, to then fit all of this inside the standard Kalman filter and get what we want. So transition function, as you can see, is divided in 2 blocks, as we see before. So there is a part that regards the robot position, and the other part regards the map, basically, so the set of landmarks that we are estimating. The robot is moving according to the Euler integrated unicycle model, so the same that we see before. Then we have all the set of landmarks. Now, a point in space doesn't move over time, right? So there is no transition, or better, the transition is just the identity. Also, no controls are applied to a landmark because there's a fixed point in the world. It cannot move by its own, okay? It's not animated. Okay, so that's our transition. So it keeps exactly the same estimate that I have in the previous time step. So the controls are affecting just the robot location as it should be, okay? Measurement function. Now, here there is a slight modification in the sense that now, to predict the observation related to the landmark, we cannot use any more points in the map with no location. Actually, those points are inside our state. So the prediction at time t related to the position of the robot observing landmark with index n, okay, in position n in my state, is this guy. Is exactly the same equation, just in this case also this piece is part of our state. So as you can see now, the prediction is done without any known quantity. We actually want to estimate all the terms inside the h function, okay? And that's the usual equation that we see also before. This, of course, will change the structure of the Jacobian in the observation model, okay? So we have to add an extra piece to take into account this guy. Control noise, same as before, so same robot, same kinematic model, same controls, same noise model. So we have the constant term, and then we have a term which is proportional to the square of the velocity, as we see in the previous two exercises. Okay. Measurement noise, as usual, in the case of a point sensor, each observation is two-dimensional, so we assume that the measurements are distributed like a bidimensional Gaussian. So these are two constant terms. The variance is equal for the x-coordinate and for the y-coordinate, and there is no correlation because that's fully diagonal. Okay, so nothing new until now. Now, we define the domains, transition function, observation functions. Now we have to speak about Jacobians. Okay. So for the transition model, right, now we have to derive this guy, and the output dimension of this guy is now 3 plus 2 times n, where n is the number of landmarks that I have in the state at time t minus 1. Pardon. Okay. So now when I'm computing the A matrix, I'm deriving this guy by this guy. Okay, so there will be state dimension by state dimension. But now look at the structure of this block. So these block columns will be the derivative of the function with respect to the robot parameterization. And this block is exactly the same as the one that we see in the previous exercise. So we have this block over here, exactly the same as in localization. And then we have the derivative of this guy with respect to the landmarks. Okay. Now we say that actually the landmarks are not moving, so our prediction is basically saying, okay, at time t, this location is equal to the one that you have at t minus 1, right? So if I derive this guy with respect to itself, I get an identity block. So each of these block columns will be n, dimension of the state, not n, dimension of the state times 2. So I have this block column for each landmark. And inside this block column, I will have a two-dimensional identity in the position in the state where I have this landmark. So for instance, if I have landmark number 2 here, so I will have here 3 zeros because these represent the derivative of the robot location with respect to the landmark. So 0, the landmark doesn't appear in the transition of the robot. Then I will have another block of 0 because I'm deriving this landmark with respect to the first landmark with respect to the second. They are not correlated in the transition, so it means that this block will be 0 here. And then I have the derivative of this guy with respect to itself, so I will have an identity. So actually you can imagine that this Jacobian is basically, it have all identity blocks around, and actually the only piece that depends on the state is this guy over here. That depends on the state and on the controls. Okay. Is that clear more or less? Or if you want me to re-explain it in another way? Let's see. Okay, nice. So, and that was the A Jacobian. So by now it's pretty clear that the A Jacobian have dimension state times state. Okay, no matter how the state is composed, that's always the dimension, of course. Now the B Jacobian, so the Jacobian of the transition with respect to the controls is always bidimensional, so I will have state dimension times 2, so the control dimension. The state is always 3 plus 2n, as before. But what you notice here is that actually just the block regarding the robot location depends on the control itself, because of course the landmarks are not actuated, right? So here actually we have the Jacobian of the localization problem, and then we have a gigantic block of zeros basically under that. Okay, that's the structure of the B Jacobian. Now the measurement. Okay, So I will ask you this. What's the dimension, the total dimension of the C Jacobian if I observe just one landmark? Okay, so what's the dimensionality of C? Write it on the chat. Yeah, okay, the derivative, they can do it. Yes, right. I want to know if they understand the dimensionality. So if someone can try to guess. Of course, the observation here, we are predicting a point. Huh? Giorgio, make the guys reply. Nope. It's not 2 by 3. 2 by 3 is the one for the localization, right? So you are deriving the prediction of the point with respect to the robot location. But now we have something else inside the state, right? Now X is not just the robot location. 2 times 3 plus 2. Yep. So it's fine. If I have one landmark in my state, it's fine. Yes. Yes, 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 yes. Nice, Yonut. I always hope to pronounce correctly your name. Akshay. Nice. Really nice. Of course, if I have n landmarks, I have 3 plus 2 by n. Okay. But for one landmark, that's the structure. So I will add the 2 by 2 block for each landmark that I have in the state. Okay, so it's always dimension of the observation times dimension of the state in that time instant. Okay, so and now xt is part of the state. So what's the block structure of this Jacobian? Like if you have to look at it, if I have an observation related to a landmark and I deriving to the state, my prediction regards just that landmark. It means that if I derive the prediction with respect to any other landmark, the derivative will be 0, right? So the structure of the C matrix for a single observation will be to have a non-zero block here, which is exactly the block that we see in the localization problem, and another non-zero block at the index that correspond to the landmark that I'm observing. All the rest is 0. So the C is actually pretty sparse, okay? So I have just 2 blocks which are full. All the others are zeros for a single observation, as you can notice here. Now the derivative, as Giorgio suggests, I will let you compute it, so I will try to skip it as fast as possible. But of course it's pretty easy. Like one block you already have it, you have just to derive the prediction with respect to the landmark. So it's really, really easy. Okay. Now the data association problem. Okay. So what's the data association problem in mobile robotics in general, I would say. So is the problem of determining the things that I'm observing in a certain point in time. Like I'm observing a point and I have a set of points in my state. So I am estimating a map in the meanwhile. Now, what I observe in this point in time is something that I already see before or is something new. And if it's something that I already see before, what is it? So which part of the map is related to the observation in this point in time? Okay. I don't know if I can express it well, more or less. You guys tell me if it was clear. So I'm seeing something. The problem with the association is understanding what I'm seeing. If I already see it before, if I never see it before, what is it exactly? So which block of my state is involved? Thanks, Giorgio. I feel also confused when I say it. So you have to determine the piece of your state that is related to the correct measurement. For instance, I get an observation about the point, okay? ZT. This is a 2D location of the landmark. Now imagine for a second that I don't have the IDs, okay? So I cannot determine uniquely how the observation relates to the map, so to the landmarks, right? The problem of data association is basically the problem of determining these IDs, okay? So to associate to each measurement and to each landmark an ID so that I can relate them in my filter for saying, okay? More or less. Yeah, okay. But as Giorgio said, it is more concise, okay? So the data association at this point can be seen as a function. So given the third measurement here, right? Like this is the gigantic vector that we see in the previous exercise, where we stack all the observations about the landmark. And this is the gigantic vector of all the predictions that I made about the landmarks that I have in my state, okay? So this is dimension n, with n is the number of landmarks that I have in the state. M is the number of landmarks that I observe in this point in time. And the data association problem can be seen as the problem of determining a function that, given an index in the measurement vector, returns the index in the prediction vector of the corresponding landmark. So it associates a measurement with the landmark inside my state, okay? So it's the same as the IDs that we see before, but now we have to construct a function that give us those IDs, okay? But for now, this is left to the next lecture. So in the next lecture, the professor will explain to you the data association problem, like how to formulate it as a probabilistic problem. So now we assume to have the assignment. In this case, the assignment means that I have something that, given observation number 3, tells me, okay, observation number 3 relates to the landmark that you have in your state in index 5. I don't know. So this is what you see here. Like, I have the first observation, so I extract from the gigantic vector of the prediction of the landmark for which this measurement is related, okay? So that's giving me an index, and I extract this element from my prediction vector, okay? And I repeat that for m observations. What if the landmarks are identical? You typically merge them, okay? Like if they are identical, I think you mean you have two landmarks with the exactly same location or really similar location. In this case, you assume that there is just one landmark, typically. So you merge the two estimates somehow. For a landmark, you can do even just the mean or the average of the coordinate, okay? But we will see later. So, now populating the map. Now let's try to resemble the different steps that we will face while we are performing SLAM in this environment. So as always, differential drive robot to the landmarks. So at the initial state, we have just the robot location, initialized with the mean and the covariance. So it's kind of a prior distribution that we have, okay? And these are the two maps that we are interested in to associate the measurement with the landmark. So we have ID to state map. So the observation is indexed through the ID. So from this ID, we want to know what is the position of the state, okay, of the corresponding landmark. And we have also the inverse mapping. So given a landmark in my state and a set of measurement, I want to know which landmarks relate to which measurement, okay? So initial configuration. Now we move, okay, so we observe landmark with ID 7, okay? And we know that this landmark have ID 7 because the data association is already made. Now we add this guy inside our state, okay? So the state is extended by the 2D coordinate of this landmark. Now we have to fill the maps. Remember that in this case, the maps represent just indices, okay? Just the index of the measurement, how to relate to which index in my state. So ID to state will be, I have ID 7, okay? So given the landmarks number 7, this is placed in position 1 in my state. 1 with respect to the IDs of the landmarks, of course. So this guy, okay? in the inverse mapping, what I have, so given the state index, that will be 1, I have the corresponding ID of the landmark or of the measurement, okay? So 7. So 7 position correspond to position 1 in the state. Position 1 correspond to ID 7. Direct mapping, inverse mapping, okay? Now I observe a second landmark, and this landmark have ID 9, so same trick as before. Extending the state, now I take from the direct map in position 9, because the ID 9 is this guy, and this landmark, so this observation is inserted in position 2 inside my state, so here I will place a 2, and here I will place the 9, okay? So that I can directly access to both. So given the ID of the measurement, I can know the landmark and vice versa, okay? 3, exactly same joke, okay, as before. Extending the state, filling the ID to state map, so ID 1 correspond to position 3, filling the opposite, so position 3, landmark ID 1, okay? So I extend it all the time that I see something. Of course I do that if I observe a landmark that I don't see before. If I'm re-observing the same 2D position, I'm refining its position through the Kalman filter mechanism, but of course I'm not extending my state, and of course I'm not updating the maps, because the IDs and the indices will stay the same over time. So this is an operation that actually you have to do one time every time you observe a new landmark, okay? Okay, so as I was telling you, we can divide basically 2 cases. I observe something that I already see, so I can use this measurement to perform a correction step inside the Kalman filter. So I will extend my state, I will not extend my state, sorry, I will insert the observation inside my C matrix and perform the Kalman update. The second case is that I observe something that I never see before, okay? So in this case, I cannot correct something, right? Because I don't have it in the state, so I cannot correct. So what I will do is that this measurement will be like frozen. I will perform the update for all the landmarks that I already know, and of course for the robot position. Then after I perform the correction, I will extend the state to include this new landmark, of course. And the covariance of this new landmark will be initialized with the covariance of the measurement that generates this landmark in my state, okay? So will be initialized using the sigma z that we see in the measurement noise model before, so with a constant value, okay? Hands-on, even in this case. So the difference that you see here, we have always the poses, transitions, the observation. The IDs, as I said, are already known, so every time we observe something, someone already solved for us the data association problem. So we already know what measurement correlate with which landmark, which measurement correlate with which landmark, okay? But we don't know the 2D position of the landmarks at any point in time. So we have to construct the map while we are moving, and this of course adds an extra complexity to the problem. So now we have another coding session on the same Meet, but if there are any questions about the data association, about the extension of the state, just ask me here, so that then we are ready to pass to the coding part. Yeah, like if you pull this morning, there is already the exercise for SLAM actually. Okay, so I will close the stream now, and we will switch to Google Meet. Okay, bye guys.